All right. So, like I said, today we're going to be talking about exponents. On the exponent properties, we call graphing exponentials too. Okay, so we're hitting kind of doing quite an overview here of exponential stuff. All right. So, let's get into it here. Zoom out maybe a little bit. There we go. And so we'll just say like, we'll call this like exponents and exponential functions. Okay. So let's kind of remember here, right, some of our exponent properties. So let's see here. Well, for example, let's maybe go back to some like really basic stuff. So for example, if we have 2 to the third, all right, what does an exponent really mean? Right? What does it mean when a number has an exponent? What is that like? What do we do when we have that? What do we do here? Cole?
Whatever the base number is, you multiply it by itself, the number of times that exponent.
There you go. Perfect. Yeah. So 2 to the third then would be 2 times 2 times 2, right? And that's equal to 8, right? And so then 2 squared would be 2 times 2, which then just be 4. And 2 to the 1, well, that's easy. It's just 2. And so there's just 1, 2 there, so we get 2, right? And so kind of like using this, idea, we can kind of make some sense about why some properties that otherwise maybe are weird, right? We can kind of make some sense about why those properties actually do make some sense. So for example, right, when we talk about raising something to the 0th power, now our rule kind of is like, well, how do you multiply something by itself 0 times? Right? How do you do that? What does that even mean? Like 2 to the third, that's easy. Like, Cole said, 2 to the third, just multiply 2 times 2 times 2, 3 times. 2 to the second, times itself 2 times. 2 to the 1, just 1, 2. But now 2 to the 0, right, we might be tempted to say, oh, that's 0 or something else or who knows here. But again, you can kind of see in the pattern, right, that as we lower our exponent powers by 1 each time, what's happening to the value of this expression, I guess? It goes from 8 to 4, which is 1/2, right, or divided by 2, and then 4 to 2, still 1/2 divided by 2, and so it only makes sense then that for 2 to the 0, which we're not really sure, divide that by 2, and it gives us 1. Okay? So there, by kind of like a pattern argument, you can kind of see why we say that 2 to the 0, we want it to be 1, and so we just say, okay, it is 1, okay? And anything, in fact, to the 0 power is 1. Except for 0 to the 0, that would be an indeterminate form. Okay. So then also, it will help us to make some sense of things like 2 to the negative 1, because again, 2 to the negative 1 doesn't really follow this pattern, right? How do you multiply 2 by itself negative 1 times, right? So that doesn't follow that old kind of definition that we have, but it does still kind of fit into our pattern here. Again, right, we're lowering our exponents by 1 each time, and so each time we do that, we're dividing by 2, or multiplying by 1/2. And so 1 divided by 2 gives us 1/2. Okay, so that kind of gives us a reason or an explanation for the whole idea of like 2 to a negative exponent. Why does that really go down into the denominator, right? Well, it's really because, as we're kind of following this pattern here, it kind of fits the pattern to say that's 1/2. Same thing with 2 to the negative 2, right? We'll divide this once more by 2, we get 1/4, but that's really just 1 over 2 squared. And so again, you can kind of see, by starting with something that we know is true, based on our understanding, right? 2 cubed is 2 times 2 times 2. We can then kind of use patterns to help us figure out some of the more interesting or strange exponents, okay? 0, 2 to the negative 1, stuff like that. All right. Of course, we have other properties as well. So for example, and I think, right, okay. So we have something like 2 to the third times 2 to the fourth. Okay. What does that equal? 2 to the what? 2 to the 7, that's right. Yeah, we add our exponents. Remember, again, the reason for that, 2 cubed, as Cole said, is 2 times 2 times 2. 2 to the 4th is 2 times 2 times 2. Okay, 4 of them. But it's all multiplication, right? And so we got 7 2's there, and so it's just 2 to the 7th, which is the sum of those exponents. Right? Let's see here. Similarly, right, if we have 2 cubed to the 4th, 2 cubed to the 4th, all right, how do we simplify that, right? Well, we kind of already talked about it. Most of you guys already know. But again, if we use Cole's explanation here, definition, the 2 to the 3rd to the 4th, that means it's 2 to the 3rd times itself 4 times. So you can say 2 to the 3rd times 2 to the 3rd times 2 to the 3rd times 2 to the 3rd. Right? 2 to the 3rd 4 times. Which now, this, right, this is the same thing, like the same kind of property as this. We're multiplying, so just like here when we multiply, we added the exponents. Here when we multiply, we'll add the exponents. 3 plus 3 plus 3 plus 3, 2 to the 12th. Or alternatively, right, you can multiply those exponents there. And again, if I'm going too fast, let me know. I'm kind of breezing through this because I feel like many of you have seen this already, but I just wanted to kind of refresh it. But again, if I'm like, just like blowing your mind right now and you're like, not sure about life. Oh, we have a cricket on the ground too. Very nice. We have a little menagerie in our classroom right now. All right, got a fly flying around, got crickets. All right. Anyway, maybe a mouse will show up too, right? We'll be lucky if that happens. All right. I just scared everyone. They're like panicking now. Okay, so 2 to the 4th over 2 to the 3rd. So now we're dividing, right? And of course, when we divide with exponents, how do we simplify them? What do? Subtract the powers, as long as we have the same base, right? So common base, we're doing division here, so that'll be 2 to the 1. And again, it kind of makes sense, right? When we multiply that have the same base, we add the exponents, so it only makes sense that when we divide with the same base, that we should subtract the exponents. And in fact, that is correct. I don't know why I put an equal sign there. Okay? So, let's see here. So let's just do like a quick, you know, example here. We'll just say simplify, you know, we'll just say simplify. It's a very nebulous term. Sometimes, you know, we're not really sure what that means, but hopefully this will make sense. So we'll do this one here, 2 to the negative 9th over 2 to the negative 7th times 2 to the negative 5th. Two to the negative 9th over 2 to the negative 7th times 2 to the negative 5th. So, let's see here. Well, again, there's a couple different ways you could go about doing this. It's up to you. I'm going to simplify this denominator here. So we have 2 to the negative 7th times 2 to the negative 5th. We're multiplying, so we add exponents. It becomes 2 to the negative 12th, and then 2 to the negative 9th in the numerator there still. Okay. Let's see. We have division, right? So I can subtract these exponents. So negative 9 minus negative 12. Same thing as plus positive 12, so it's going to come 3. So it's 2 to the 3rd, which is then just 8. Okay. Okay. Oh, now he's really going fast. Oh, he stopped now. Okay, good. So there's it. 8. Yeah, you can just drop it there. That's fine. Thank you. Okay. So let me give you one to try. Alright, so same thing. Try and just simplify here. A over b squared, that quantity to the negative 2, times a squared over b, that quantity to the 3rd. Okay. So give that one a shot. Yes, I gave you variables and more complicated stuff. Let's try. So yeah, give this one a shot here. And try to simplify so that you have no negative exponents. That is one of the traditional kind of things that you would do for a problem like this, okay? You want to try and simplify it so that you have no negative exponents. Again, simplify is kind of a nebulous term, but that is a kind of a typical way to go about doing it. So try and simplify so that you have no negative exponents. Solving this, there's a couple different paths you can take about how you solve them. So, I mean, it's really, and sometimes one way is kind of better than the other, and sometimes it's not. So, it's not, I don't know, you just kind of get a feel for things sometimes, too. Okay. Still see some people working here, so I'll give you like another 30 more seconds here. All right, let's go to Robert. You got something for us here? What did you do here? Okay, so we distribute the -2 there, so a to the -2 over b to the -4. Okay, so far so good. And then you do the same thing for this fraction, I'm guessing? For this as well? Okay, so that'd be a to the what here? A to the 6th over b to the 3rd. Alright, and then what do you do from here? Okay, so you multiply. So you're multiplying here, and you then combine those. I got you. So we multiply here. A to the negative 2 times a to the 6 gives us a to the 4th. Okay. B to the negative 1 in the denominator. Okay. Which then, without to get rid of that negative exponent, what can we do with that b? Not sure. Okay. So b to the negative 1. One way to think about this, b to the negative 1 is the same thing as 1 over b, right? So far so good, yeah? You're okay with that? B to the negative 1 is 1 over b. Yeah. So instead of dividing by the fraction 1 over b, instead of a to the 4th divided by 1 over b, we can instead multiply a to the 4th by the reciprocal of 1 over b. And what's the reciprocal of 1 over b? Just b, yeah. So this could be a to the 4th b, or b to the 1, depending on how you want to write that there. There it is, yeah. Again, b to the negative 1, right, just like we set up here, 2 to the negative 1, 1 over 2, b to the negative 1, 1 over b. But instead of a to the 4th divided by 1 over b, right, that's, we have a fraction within a fraction, what can we do to fix that? Well, dividing by a quantity 1 over b is the same thing as multiplying by its reciprocal, b over 1, or just b. So there it is. So that's one way to do it. Did anyone do it in a different kind of fashion? Anyone do it differently? You want to share? There are a couple of different ways to go about doing this one. No one wants to share? Okay. So anyway, simplifying exponents, right? That's that. But our main focus actually for today, okay, so I just wanted to kind of refresh our memory a little bit about exponents and things. But our main focus for today is actually not this. It is exponential functions. Okay. And an exponential function, all right, is a function, we'll call it f of x here, that can be written in the form a times b to the x. Right. An exponential function has the variable x, or independent variable x, in the exponent here, in the exponent. Okay. And of course, this is true for, we have to make some stipulations here. So first of all, we want to stipulate that b is not equal to 1. Okay. What would happen to our exponential function here if b was 1? Why do we have to stipulate here that b is not equal to 1? What would happen if b was 1 here? What would we get? Done? Yeah, it would just be f of x equals a, right? Because if we put a 1 in here for b, 1 to any exponent is 1, and that would just always be 1. So it's really just going to be graphing the constant function f of x equals a. So that's why we stipulate here that b is not equal to 1. Yes, we could graph it if b was 1, but it wouldn't be an exponential function. It would just be a constant function, right? Okay, simultaneously, we also need to stipulate that b is greater than 0. We obviously can't have b equal to 0, kind of for the same reason why we can't have b equal to 1. If b was 0, it would be 0 to an exponent, which again would just be the whole thing would be 0. It would just be graphing, you know, the horizontal line y equals 0. But we also don't want b to be negative because that's going to like really cause some issues. Because for example here, if b were like negative 1, well imagine these x values here could be any x value. So for example, we could have an x value of 1/2. And if we had a negative 1 for our b and we raised it to the 1/2 power, well now we're talking imaginary, right? Because negative 1 to the 1/2, that's the square root of negative 1. And so we can't have these negative values for b in here. That would like kind of mess up our graph. So we need, in order to have a nice, smooth, continuous graph, we need to stipulate also that b values must be greater than 0. So b can't equal 1, and also b needs to be greater than 0. So what does that leave us then? What numbers do we have to pick from? So, well, we're going to talk about one case here. We'll talk about the cases where b is greater than 1. Okay, cases where b is greater than 1. Okay, so as an example here, we'll look at f of x equals 3 to the x. Okay, f of x is 3 to the x. And again, I feel like you guys have worked with these things before, so I don't want to, I'm not going to dilly-dally too much on this, but, we want to graph this, okay, is our idea, is the question here, is the thing to do, okay, so we want to graph this. So let's just kind of examine this thing. F of x equals 3 to the x, let's make a table of values here. So let's see, we're going to figure I'm going to do a horizontal table. All right. And of course, since we're dealing with an exponential here, right, we want to be very careful about the x values that we select. For example, an x value of 10 would be an unwise choice here, because then you have to calculate 3 to the 10, which is too intense. So we'll start with something like, I don't know, I'm going to do some negative exponents here. It's like negative 2, negative 1, 0, 1, 2, and yeah, I'll go to 3. And of course, so we'll start with the easy ones here. 0, right? 3 to the 0, that's 1. 3 to the 1, well, that's 3. 3 to the 2, that's 9, right? 3 squared is 9. And then 3 to the third, that's easy. It's also 27. But of course, those negative exponents, they're not too bad, especially now that we have these here. We can kind of see, okay, we're dividing by 3, dividing by 3, dividing by 3. So dividing by 3, it's going to be 1 over 3, right? 3 to the negative 1 is just 1 over 3 to the 1, or 1 over 3. And then this one will be 1/9. Okay. Out of curiosity here, what would the domain of this function be? What would the domain be here? Or another way of asking it, right? Are any of our domain restrictions possible? For example, is it possible for us to divide by 0 in this case? When you have 3 to the x, is it possible to divide by 0? Okay. Or could we take the square root of a negative in this case? Do we have any square roots here? Yeah, no, not really, right? I mean, we could plug a 1/2 in here for x, right? X equal to 1/2 is possible, but 3 to the 1/2, that's not a problem. It's going to be 3. So whatever we're working with here, we're always doing it to 3. So we're never going to divide by 0, and we're never going to take the square root. So the domain is all real numbers here. It's negative infinity to infinity. There's no problems. Okay. There's no problems. All right, we'll also talk about the range here, but we'll hold off on the range for now because I want to go ahead and just graph it to get an idea what the range might be. So let's graph this thing to kind of get an idea of what we think maybe the range will be here. And yeah, I'm going to try and squeeze it all in here. So let's see. So I'm just going to put about 5 tick marks on either side and above and below the origin there. Okay. For the x-axis, it's probably okay to just count by 1s. For the y-axis, we probably shouldn't count by 1s because we got to go up to 27 here. All right. And so I'm going to count by 5s. Again, when it's your graph, you can count however you want there. All right. And so we'll just plot the points, right? So negative 2, 1/9. All right, I'm going to get a little creative here and say the 1/9 is like right there. And then 1/3 at negative 1. So again, just slightly above that, but not much. And then 0, 1. Okay, so slightly above that one. Okay, 1, 3. Okay, that's a little bit better. It's like, now we're seeing some movement here. And then 2, 9. That'll be just below the 10. And then 3, 27. So 3, 5, 10, 15, 20, 25, 27, we'll say right there. Alright, so there's my 3 points. And of course, now that you have those 3 points, you kind of get an idea about the shape of that graph, right? Not 3 points, so there's a couple of points there. And so we can kind of just like trace this thing and see that it's going to... So what do we want to say, now that we have kind of a picture of the graph here, what do we want to say the range is going to be? What do we say, Anna? 0 to infinity, very good. Anna, should we include the 0 or not? No. Yeah, we're not going to get to the 0. Okay, that's right. Welcome. Okay. So yeah, the range here is 0 to infinity, not including the 0. All right. If you imagine here going really far to the left, right, these really, really negative values of x, well, that's going to make that 3 to the negative value, so it's going to be 1 over 3. So those numbers are going to get smaller and smaller and smaller and smaller and smaller and smaller and smaller. We can expect it to go to 0, right? Kind of like a horizontal asymptote of 0 as you go to the left. Okay, so as you approach negative infinity, the horizontal asymptote is 0. But as you go to the right, we have an end behavior that goes to positive infinity, obviously, there. Okay, but that's the idea. In fact, you can apply the horizontal asymptote kind of rules to this thing to help you realize that there will be a horizontal asymptote as x approaches negative infinity. Okay. All right, let's see. Again, just some other things, right? Do we have, I guess, this kind of, do we have any x-intercepts here? Yeah, no, right? If you think about it, right, an x-intercept is when you have x comma 0, right? When you have 0 for your y-coordinate. But we just said the range, the y-coordinates don't include 0 here, so there won't be one. Okay? 3 to the x never equals 0. Okay, it gets really close, but never equals 0. And of course, we already found the y-intercept, which is, 0 comma y. It's the point, 0, 1. Okay. All right. Again, pretty straightforward stuff there. Let's take a look at the next case, right? The other case. So we have the cases where b is greater than 1, but then we also have those numbers. So that covers like everything greater than 1, but we also have b values between 0 and 1, right? So we want to look at those as well. Okay. So we'll look at that here. So cases where 0 is less than b is less than 1. Okay, and for this one I won't get too creative here. I'm just going to say f of x equals 1/3 to the x. Okay. It's 1/3 to the x. All right. So again, let's kind of get an idea about this. We'll use a table here to kind of help us out, get some points. And I'll use maybe the same x values here. So I'll start with like a -2, -1, 0, 1, 2, and 3. Okay. So now when we go to plug this in, well, let's do some easy ones here. So for example, 0 plugged in for the x, right? 1/3 to the 0, we know that's got to be 1, right? Anything to the 0 power is 1, except for 0. 1/3 to the 1 power, that's going to be 1/3 as well. Okay. 1/3 squared, 1/9, right? 1/3 times 1/3, and then 1/3 times, or 1/3 to the third will be 1/27. 1/3 times 1/3 times 1/3. One-third to the -1, what's that going to be? What's 1/3 to the -1 power? You can kind of get a hint here if you look. I mean, as you go from 1/27 to 1/9, from 1/9 to 1/3, from 1/3 to 1, Anna, what should it be? Yeah, it's going to be 3, exactly right. Okay. Right? 1/3 to the negative 1. Anytime you raise something to the negative 1 power, you can think that that's just the reciprocal, right? Something to the negative 1 like that, so it's just really going to be 3 there. And so then, likewise here with to the negative 2, 1/3 to the negative 2, what should that be then? What will that equal?
9.
Yeah, 9. That's right. Yeah, 9. Okay. And so then, likewise, we can graph. Well, let's talk about. Actually, I don't want to graph just yet. So then, like, what's the domain of this one? Okay. What's the domain for this function? Are we going to hit any domain restrictions? Could we divide by 0 here? Could we take the square root of a negative here? Are either of those possible? Yeah. They're not. No, they are not. Okay. This number is always going to be 1/3. The only thing that's changing is the exponent. So positive values, negative values, 0, all those will be okay when you do it to the 1/3 there. So the domain's negative infinity to infinity. Let's graph this then and talk about the range. Okay, again, we'll sketch a graph. Thanks.
You're welcome.
Okay. And again, we'll count by 1s on the x-axis, 5 on the y-axis, just to kind of keep it easy here. And let's plot these points. Let's see here. 0, oh, we'll use a different color. 0, 1, 1, 1/3. Okay, so like the 0, 1, 2, and 3, kind of hard to graph because they're so tiny in our scale and stuff like that. But negative 1, 3, okay, we can graph a little bit better. And then negative 2, 9, we can graph a little bit better too. And of course, you can imagine negative 3 will be, 27, so something like that. So again, looking at this graph, what does it look like our range will be here? What do you say? What does it look like our range is going to be? Let's see here. Emily K., what do you say? Negative infinity to 0. Close. What's our lowest y value? I think you start at negative infinity. If you look here, our y values don't go down to negative infinity. So it's going to be, so we'll start at 0 and then go to infinity. Yep. So it's the same range as before. Same range as before. Right? In fact, if we think in terms of transformations, if I go back to the other graph here, how are these two graphs related, transformationally speaking? Like, how could I get this graph from this graph? What do we got to do there, Isaac? Over the y-axis, exactly right. These are reflections over the y-axis, right? And remember, if we think about those transformations, 1/3, remember, is 3 to the negative 1. But then we have a power to a power here. It's 3 to the negative x. And remember, how do you reflect something over the y-axis? Well, it's the same function value, but it's just the opposite x value. See? So here, this x value gives the y value. Here, it's the negative x value and the y value. So it's a reflection over the y-axis there. Follows those rules. Okay? Exactly. So, speaking of reflection of the y-axis. So, speaking of transformations, that's the one last thing here I want to talk about. Again, I think this is something you guys have seen before, so I don't want to spend too much time boring you, but again, some of you were like, too late, Mr. Witt. I'm bored. Alright. So let's just talk about the function f of x equals 2 to the x. Okay. And compare it to g of x equals 2 to the x plus 1. Okay? So adding a 1 on there to our 2 to the x at the end, what type of transformation is that going to result in? What's that going to do to our graph? What do you say? Putting that 1 on at the end, what's that going to do? What's that? Shift it up. How much? Yeah, exactly right. Okay? And of course, if we wanted to shift it down, we could then do a -1 or -2 or whatever you want to shift it down by. Exactly right. Okay, good. Let's see here. If I have g to the x equals 2, and now I'm going to put it 2 to the, I'm going to put an x minus 2 in the exponent. What kind of transformation is this? To the right. Very good. Shift right 2. Okay, remember when you have that number in with the x, it's like the opposite of what you would intuitively expect, right? X minus 2, we think left 2, but really it's right 2. Okay? And then g of x equals negative 2 to the x. Okay, so I kind of want to, let's see, I want to be careful how I write this, because there, we'll do it like that. What kind of transformation will that result in? Flip over the x-axis, yeah, so a reflection over the x-axis, yeah. And then, of course, if we had g to the x equals 2 to the negative x, like we saw before, that was our flip over the y-axis. Right? Okay? 2 to the negative x is the same thing as 1/2 to the x. So. Okay? And I think we'll stop there and get you guys started on your assignment. I think you have everything you should need. All right? So we'll stop there. Get you guys started on your assignment.